Hello, this video is for Stat 310, Handout 6, Part B. Okay, let's go ahead and get started then. So in Part A, we had a discussion about the overall test and also the individual effects. In Part B here, we are going to be considering the multiple comparisons. The data that we're using for Handout 6 is a study about sleep deprivation. It is at 4 levels, 12 hours, 18, 24, and 30. And here are the data values for this particular experiment. This is the plot that we get from the JMP package. We can see again the overall effect and then the individual effects or averages. So what we learned in Part A again was we did the overall test, which was just testing whether or not there was any effect. And our conclusion from that test was that we did have enough statistical evidence to say there's an effect due to sleep deprivation on the average number of touches. The p-value that we would use for that is underneath the analysis of variance, and it's that quantity right there. We also talked about the individual effects under expanded estimates, and that just allows us to see which levels have a significant effect off of that baseline or overall average of 4.25. So what we're going to do with the multiple comparisons is, let me show you the graph down here first, is we are going to want to compare the average from 12 hours against the average from 18 hours. So is there a statistically significant difference in this green line compared to this green line? We also could compare 12 hours to 24 hours. So that is indicated here by B. So another test that I could look at is the average at 12 hours different than the average at 24 hours? Or is the average at 12 hours different than 30 hours? Because I have 4 different sleep deprivation levels, I have a total of 6 tests that could be done for my pairwise comparisons. So by pairwise comparisons, we just mean we're going to compare one level of sleep deprivation to another. And again, there's going to be a total of 6 of those comparisons. So we could actually do these analyses, okay, using Handout 4. Because in Handout 4, I just compared averages from 2 different groups. I mean, that's what Handout 4 was about. Is suppose I had 2 groups, how would I go about comparing the average? And I would do just a standard t-test there. So I could do a t-test between 12 hours and 18 hours to compare the average here to the average here. So that's what we did up above here. Is I am comparing 12 hours here to 18 hours. And our standard t-test is here. If I use 2-sided p-values, my p-value is going to be 0.5036. And is that less than 0.05? No, it's not. So what that means is I do not have a difference in the average at 12 hours compared to the average at 18 hours. So if we go back down here and look at that, this green line is just too close to this green line in order to say that they are statistically significant from one another. If I look at the 12 hours versus the 30 hours, though, that is going to be test C that I have labeled here, and that's going to probably be significant because that's a pretty big jump between this average and this one. So let's look at test C here. So again, this is going to be 12 hours compared against 30 hours here. And the p-value here is indeed less than 0.05 as I anticipated. It's at a level of 0.0001. So there's a statistically significant difference in the average number of touches between 12 and 30 hours of sleep deprivation. Other ones that are significant here are going to be, let's see here, 18 hours compared to 30 hours. So again, that's a pretty big jump between those two. So that is test E, 18 hours to 30 hours. That's going to be test E here. Okay. And also it appears that when I compare the 24 hours to the 30 hours, I get a statistically significant result as well. So of these 6 tests, okay, I can say that I have a difference between 12 hours and 30 hours. I can say that I have a difference between 18 hours and 30 hours. And at least with this approach here, I can say that I have a difference of between 24 and 30 hours. So again, at that 30 hours, we really see a pretty substantial jump in the number of on average, the number of touches that we're going to see here. Okay, there is one caveat though in those tests that I just completed, or there's one issue that comes up. And that is the family-wise error rate. So that's an important idea here that we're going to talk about now. When we do lots and lots of tests, each at a 5% level, when I get all done with all of my comparisons and all of my tests, I am not going to have a 5% error level anymore. Okay, so if I do this table here, let me see if I can get that whole thing on the screen. What I did was a total of 6 different tests here. If I do each one of those at the 0.05 level, my maximum error rate is not going to be 5%, but it's going to be 30% because I did 6 tests. That is our family-wise error rate. The family-wise error rate becomes a problem when you are looking at multiple tests in order to arrive at a conclusion. My conclusion that I arrived at up above was that, what did I say again? That the 30 hours was substantially higher than 12, 18, and 24. Or at least it was different. So I used 3 different tests in order to make that decision. And then I could also say that none of the others were statistically different from one another. But I did 6 tests, right, to come to that conclusion. My overall error rate, or my maximum error rate, is not 5%, but instead it's 30%. We want to control or keep track of or keep in check that maximum error rate. Now, one of the really simple things to do, okay, and this individual that came up with this doesn't get enough credit, I don't think, and that is called the Benferroni adjustment. What the Benferroni adjustment does is instead of using 0.05 as your cutoff threshold for your p-value, let's use 0.05 divided by 6 because I'm doing 6 tests. That was pretty clever because now my maximum error rate here is going to stay at 5%. It turns out when I use the Benferroni adjustment to do my comparisons though, the sleep deprivation comparison between 24 and 30 hours is no longer significant because this p-value, 0.0114, is not less than the 0.0083. So what Benferroni adjustment does is it just takes that threshold value that we use to compare our p-value to and just reduces it depending on how many tests we're going to use. Okay, and that's a pretty simple adjustment. There are better adjustments that can be done, or ones that are more commonly used, and the one that is most commonly used is one called Tukey's Honest Significant Difference, or HSD. Now, if a statistical procedure has the word honest in it, it's probably a pretty good procedure. There are other procedures as well inside of the JMP package. So we could ask for the, I think Dunnett's is another one that JMP includes. We may talk about that one later. So what did we learn here? We do not want to do just a whole bunch of individualized tests and not make an adjustment for that maximum error rate. You have 2 choices. You can either use something simple like Benferroni's adjustment, or you can do your comparisons using something called Tukey's honest significant difference. What we're going to use inside of the JMP package is this Tukey's HSD. Okay, so when I'm inside of the JMP package, so let me go ahead and just fit this model again. I have number of touches here. Sleep deprivation level is going to be my effect that I'm testing. I'll hit run here. I get all of this output, which is lots and lots of output. Here is my analysis of variance table. Again, if you want those expanded estimates, you can ask for those. So these would be the individual effects. Here's the overall ANOVA table. Over here on the right is where I can do my multiple comparisons. So let's not worry about that leverage plot. What the least squares means table is really not that informative, but what that is giving me is just the averages for each of those groups. And the least square means just implies that those averages are being computed using the model. So the overall effect plus or minus the effect for each of the individual groups. This 3, 3.5, 4.25, 6.25, those are simply just the averages of each of the groups. When I go to my red drop-down box here, you can see that I have LS means student T, LS means Tukey, HSD, or LS means Dunnett's. The LS means student T is the one, okay, that I showed you initially, and that's not going to have any control of that family-wise error rate. So we do not want to use LS means student T. The one that we're going to want to select is LS means Tukey. And I get a bunch of output here. I get these LS mean differences, which we'll talk about, and then I also get what's called the connected letters report. So we'll talk now about both of those. Okay, so again, if we go back to our notes here, student T has no correction to the overall error rate. So I might put in here, don't use this one. Don't use this one because it doesn't have, oops, don't use, there we go, because it does not have that correction for that overall error rate. Tukey's HSD is the one that we use. This is the most common one that people use. Okay, and I do have a little bit about Dunnett's here. Dunnett's would be one that you would want to use if you have a control group in your experiment, kind of a placebo or control group. All right, so let's look at our LS mean difference report here. And I'm going to first consider this information in box A. Okay. Box A is going to do a comparison between 12 hours and 18 hours. So I just line up the row in the column here. The confidence interval is given by this here where I have my cursor is the lower confidence limit, and then that is the upper confidence limit. So the 95% confidence interval goes from -2.52 up to 1.51. This confidence interval catches 0. So what that means is that there is no statistically significant difference between 12 hours and 18 hours because 0 is captured in this interval. Right? If the difference in the averages is 0, that means they're the same. Likewise, when I compare 12 hours to 24 hours, that confidence interval catches 0. -3.2 to 0.77 or 76, that interval also catches 0. But the 12 hours to 30 hours does not. So that would be this box over here, 12 hours and 30 hours, and you can see that the interval constantly is entirely negative. Is entirely negative. That means I do have a difference. The confidence interval gives me a range of likely values for the difference in the two averages, and this confidence interval right here does not include 0. It stays completely negative. So I do have a difference between 12 hours and 30 hours in terms of the average number of touches. Now it turns out that JMP color codes these, if they're significant, they're going to show up in red. So these two combinations here are the ones that are significant. 12 hours and 30 and 18 and 30. Okay. The 24 to 30 is not significant. Okay. That interval catches 0. And this is using the Tukey's HSD approach here. All right. So what do I learn here? I learn here that 12 and 30 are different from one another, and also 18 and 30 are different from one another. The 24 to 30 is close, but it is not technically significant there. And that actually, Tukey's HSD here actually agrees with what the Benferroni said. If we go back up here and look at what the Benferroni said, it said the only two that were significant were the 12 to 30 and the 18 to 30. So for this particular example, the Tukey's HSD and the Benferroni approach agree with one another. Here's a little bit of information about how those intervals are calculated. You actually use this Q value, the 2.73, okay, as the interval coefficient when you're constructing those intervals. We don't have to worry about constructing those by hand. Now let's talk about the connected letters report. So down below, if I go back to my output, down below here I have what we call the connected letters report. So let's talk through what that is. Here's what that looks like. Okay. And if the groups, okay, have different letters, then they're significantly different from one another. Okay, so what does that mean? 30 hours and 24 hours both have an A. So they are not significantly different from one another because they share a letter. Okay, how about 30 hours and 18 hours? 30 hours and 18 hours do not share a letter. 30 hours has an A and 18 hours only has a B. So those are significantly different from one another. So when I do my comparison of 18 to 30, they are statistically different from one another. And that is what I learned when I look up here, right? When I compared 18 here to 30, the interval did not catch 0. So they were different from one another. So the connected letters report is just a more simplified way of showing you which ones are statistically different from one another and which ones are not. So again, 30 and 18 are different from one another because they don't share a letter. 30 and 12 are different from one another because they don't share a letter. However, 24 and 18, they both have a B. 24 and 12, they both have a B. 18 and 12, they both have a B. So those are not different from one another. So from the connected letters report, we can identify that 12-hour sleep deprivation and 30-hour sleep deprivation, the average number of touches between those two are going to be different from one another, and likewise for 18 and 30. Okay, some final thoughts then about our analysis up to this point. The first thing that we did with the overall test was just establish that there was a difference. Okay, so the first thing we want to do, or in that overall test, is just identify whether or not there's some effect. We can follow that up by looking at the individual effects. Okay. So looking at those individual effect tests under those expanded estimates. Or more commonly, a reasonable follow-up is to identify where the differences exist. So what this overall test does is it just says there are some effects, but it doesn't tell us which ones are different from the other ones. So those multiple comparisons are doing that for me. And what do I learn from my multiple comparison analysis? Is that the sleep deprivation 30-hour level is different from 12 hours, and that the sleep deprivation 30 hours is statistically different than the 18. And none of the other comparisons were significant. So I can't say that 30 is different than 24. I cannot say that 24 was different than 18, or that 24 was different than 12, nor can I say that 18 is different than 12. And that agrees if we look at all these comparisons here. The only ones that were statistically significant were C and E, and that's where I have the biggest jump between the green lines. All the others are too close to one another. So the average at 12, 18, and 24, those are all just too close to one another to say that they're statistically different from each other. Okay, so what is part C going to include? Let's just down here finish this up. What part C is going to include is some considerations about checking the assumptions, investigating the power, and etc. And we will be back in class to discuss that particular part. Okay, that's all we have then for Handout 6 Part B. Thanks for watching.